Okay, I hope you all had a good vacation. Mine was not as good as it could have been. It involved somebody falling asleep at the wheel of a car and totaling their car, but being fine. So extra road trip to go rescue the person, and a lot of grading. Your grades, I believe, should be completely up to date. If you see any problems, and for instance, Leslie saw a problem that I did fix, if you see any problems, please let me know so I can fix them, because tomorrow we have to turn in midterm grades and I want them to be accurate. We will continue on talking about chemical bonds. We talked about bonds between molecules last class period. We talked about specifically metal bonds, which are a bond that is essentially decentralized electrons holding the atoms together. On one of the potential test question submissions, a student said, due to the weak nucleus. It's not the weak nucleus. It's the weak bond between the electrons and the valence electrons, specifically in the nucleus, that allows those electrons to move around, that makes the metal bond possible. Then we had covalent bonds. Covalent bonds are where valence electrons are being shared between two atoms. So you can form covalent bonds. And once again, actually, this might have been this. No, it was a different student's question. The number of covalent bonds you can form is equal to the number of unpaired valence electrons. So a student had a question, and the correct answer was none of the above for how many covalent bonds you can form. In this nitrogen atom, it has 3 unpaired valence electrons, and thus it can form 3 covalent bonds. And when it forms those bonds, then it's going to have essentially, from the sharing bonds, it will have no longer any unpaired electrons. It'll have a complete set of valence electrons. Now my picture, I'm going to zoom in so I can try to draw them a little better. The red dots would be the electrons being shared via covalent bonds, and then you would have, as shown in this picture here, it looks like a filled octet for the valence electrons. So we had covalent bonds, and then the next type of bond we had was, actually I may not be going in sequence of the order I lectured on. Yeah. But we had ionic bonds. What's the difference in a covalent bond and an ionic bond?
Covalent bond is... No, they're together. They combine.
Okay, you're in the ballpark. Let's see what Danny has. That's the key. Covalent bond, you're sharing the electrons. Ionic bond, you're transferring the electron, but then because one's positive and one's negative, they're attracted to each other. Covalent bonds, this diagram here is just showing that covalent bonds don't have to be single bonds. That means you don't have to have just one electron shared. You can have each atom is sharing 2 electrons and have a double bond. Or each atom is sharing 3 bonds, or 3 electrons in a triple bond. And then we talked about polar covalent versus covalent. Covalent, you're sharing electrons, sharing valence electrons. Covalent. Polar covalent is when they're sharing, but it's not equal sharing. It's kind of like, my wife and I share the garage, but it's not equal because my car's parked in there every night. Okay? It's not actually shared equally. So some atoms have a higher electronegativity, which means that they have a higher desire to get an extra electron. Some have a lower electronegativity. They don't really have much desire for an extra electron. And so that electronegativity chart is what this diagram is showing. And you see that the very highest electronegativity is fluorine. The fluorine atom really, really, really strongly wants another electron. The lowest electronegativity is down at the other end, francium. Oddly enough, they both start with F. The francium really is not strongly attached to its electron. And you see that general trend. Up and to the right is strong electronegativity. Down to the left is low electronegativity. And the difference in electronegativity between the atoms tells us if it's a covalent bond or a polar covalent bond, or if it's going to be an ionic bond. So the difference, the way we can differentiate, and no bond is perfectly covalent. No bond is perfectly ionic. There's always some amount of mixing, I suppose. Well, there may be some exceptions. Perfectly covalent could exist, I suppose. Like O2 might be perfectly covalent. But the way to differentiate, and this is where I ended our last class period, is looking at the difference in the electronegativities between the components of the bond. If the difference in electronegativities is less than 0.5, less than 0.5, then it's going to be sharing the electron. It's going to be covalent. If it's between 1.6 and 0.5, it's still going to be sharing the electron, but not very equally. And so it's going to be polar covalent. Polar covalent, one of the atoms is going to, the one with the higher electronegativity, is going to have the shared electrons more. The one with the lower electronegativity will have them less. So the one with the lower electronegativity is going to have a positive overall charge. The one with the higher electronegativity, a negative overall charge. And then if the difference in electronegativities is bigger than 2, and you notice there is a gap between these numbers just because it's kind of fuzzy. But if the difference is bigger than 2, then it's going to be ionic. Then one of them is yanking the electron from the other. They're not sharing much at all. And so we have examples up here at the top of different compounds. Each one has fluorine on one side. FF, well, what's the difference in electronegativity between a fluorine atom and a fluorine atom? That's a redundantly silly question. What's the difference? It's like asking, what's the difference in the height of Richard Webb and the height of Richard Webb? Nothing, right? There is no difference. So that one's a perfect non-polar covalent because it should have the charge perfectly symmetrically distributed between them. Then the hydrogen and the fluorine, we can just look up here. Fluorine is 3.98. Hydrogen is 2.2. The difference between those two, if you subtract them, is 1.78. 1.78, really? I swear I did my math right. Didn't I? Yes. 1.78 is actually outside of this number. I didn't check that. This just comes from the textbook. So that's going to be a very polar covalent bond. It falls in this region between the two. So which one is going to have the negative charge and which one is going to have the positive charge in the hydrogen fluoride? Which one wants the electron more, hydrogen or fluorine? Fluorine, because it is the most electronegativity of all, and that electronegative of all the atoms. It's the one that wants it the most. And so the fluorine wants the electron the most. It's going to yank it over. And so the fluorine's going to have the negative charge. And thus the hydrogen, losing most of the control of its electron, has a positive charge. So then you have a polar molecule with the hydrogen side being the positive and the fluorine side being the negative, which is what this symbol is indicating. The arrow is the direction of the negative. The plus sign is the direction of the positive. And then sodium fluoride, if we look at the differences in electronegativities between sodium and fluorine, 0.93 and 3.98, that's 3.05 difference. That's very highly ionic. Now let's just take a very common thing, sodium chloride. Which kind of bond will sodium chloride have? Those are the electronegativities. Will that be covalent, polar covalent, or ionic? Okay, Danny says ionic. Leslie nods her head. How did you determine, Danny? Okay, subtracted them, and you got something that was bigger than 2, and hence you come to the conclusion that's an ionic bond. Now I've been, question? I thought I heard somebody. I've been saying the names of these elements. What was the name of these molecules? What was the name of that molecule? This is one of the things that was going to be on the quiz. Remember I said on Friday we'd have a quiz where you'd have to name some of these? How do you determine the name? Just by looking at that. Okay, we had a couple rules. First rule was take the element that is the farthest on the left. So if you look at the periodic table, which one's farther on the left? Na, natrium, otherwise known as sodium, or F, fluorine? Farther on the left. Na. So that's why I said sodium first, because it's the one that's on the left. And then we have take the one that's on the right and change its ending to "ide." So instead of saying sodium fluorine, I said sodium fluoride. That's how we come up with that name. So if we look at the one in the middle here, HF, using the same rules, which one's farther on the left? H, so it's hydrogen fluoride. Now, oddly enough, I was reading an article people talking about chemistry, and somebody talked about this molecule. Using our rule, what should that have for its name? It should be what?
What is C?
C is carbon.
Carbon dioxide.
I did an untraditional capitalization just to emphasize the di is the number 2 and then oxide. So we have the di to tell us about the number 2, and then we change the ending ide because it was at the end, and it's carbon first. The person writing this said dioxygen carbide. I've never seen it written that way. It didn't follow the left to right sequence. But they don't always follow that sequence. That's like some general rules. And so I'm pretty sure carbon dioxide is the correct technical way. But if you say dioxygen carbide, people will still be able to decipher what it is. Okay, now we're going to talk, polar bonds don't always have to be a polar molecule. So this is showing an example of a carbon dioxide. The carbon-oxygen bonds, if we look at the electronegativities of carbon and oxygen, so going back 2 slides here, carbon and oxygen, that's a difference of roughly 0.9. A difference of roughly 0.9 puts it squarely in the polar option. The oxygen being the more electronegative is going to be the negative charge. So you're going to have a negative charge for the oxygens and positive on the carbon. So you have 2 polar covalent bonds there. How do I know they're polar covalent? Because I looked at the differences in the electronegativities. But yet this is a nonpolar molecule because carbon dioxide is a linear molecule and it's symmetrical. So it has negative at the extremes and positive at the center. but you can't draw an arrow going from the negative to the positive because it's negative on both ends. So that's a nonpolar molecule, even though it has polar bonds. So it's always important to clarify, are the bonds polar? Does that mean the molecule's polar? Usually yes, but in a case like this, no. In a water molecule is an H2O, or dihydrogen monoxide, but this is a polar molecule. The H and O bonds are definitely polar bonds. Why would one be polar and the other non-polar? Not exactly. No, so I said not exactly. I didn't say no. It's not exactly, but the key is, and the reason why it's not exactly, not no, is that this one here has oxygen as its centerpiece. That one has carbon as its centerpiece. And the symmetry for the bonds is going to be different. Carbon has 4 valence electrons. And so with those 4 valence electrons, notice that was 2 double bonds. And so it has 2 electrons going one way, 2 electrons going the other way. Forms a linear situation. But oxygen is 2 over to the right. It has 6 valence electrons. Those 6 valence electrons means it forms 2 single bonds. And then you have 4 additional electrons that aren't bonding with anything. And those 4 additional electrons make it so it bends, because those 4 additional electrons are going to repel the other atoms. And so you end up with a water molecule. I think my next picture, yeah. The water molecule is not straight. It's bent. And because it's bent, the side where the hydrogens are closer is positive. The sides where the oxygen is negative. So we had 2 molecules, each one having polar covalent bonds, but one is non-covalent or non-polar for the entire molecule because it was linear. The other one, and linear and symmetrical. The oxygen or the water is symmetrical, but it's not linear, and so it's polar. Has a positive side and a negative side. And the fact that a water molecule has a positive side and negative side, as we'll see before the end of today, is super important to things like us having life on Earth. If we didn't have this, everything would be different. And yeah, I don't think we could exist. I mean, God could figure out another way to make it exist, but me as a human, I don't have the answer to how we could exist. So if you have water molecules, why does it matter that water is a polar molecule? Well, if I have those molecules, one side positive, one side negative, let's just say I have 2 molecules, my left hand and my right hand. And let's say that my palms are positive and my fingertips are negative. If I bring them close, what's going to happen? They're free to move about so they can rotate. If my fingertips are negative and my palm is positive, they're going to go like this. So that the positive is attracted to the negative. Now, this is not a bond between atoms. This is a bond between molecules. So we need to get something clear in our minds here. When we were talking about the covalent bonds, the ionic bonds, the metallic bonds, those were bonds between atoms. Now we're talking about a bond between molecules where I had 2 dipoles. Dipoles because they have the electric charge not symmetrically distributed. And because of those dipoles, they rotate and they form a dipole-dipole bond. So that dipole-dipole bond is not a bond holding atoms together, it's a bond holding molecules together. But that's going to hold the water together. That means the water stays together more. You're going to have to raise the temperature more to make it go from a solid to a liquid. You're going to have to raise the temperature more to make it go from a liquid to a gas. So if water was not a polar molecule, at room temperature, it'd be a gas instead of a liquid. But because it's polar, these dipole bonds make it so even at room temperatures, it's still in the liquid phase. And you only have to get down to 0 Celsius for it to go into the solid phase. So the fact that it has these dipoles is really important. Okay, first clicker question. And this clicker question is not relevant to what we've just been talking about other than is comparing the carbon dioxide to water. Which is heavier, that is, has the most mass, in case you're not on Earth, carbon dioxide or dihydrogen monoxide? I see people looking back there. Let me just write the numbers for you. The mass of an atom of carbon is 12 atomic mass units. Oxygen is 16 atomic mass units. And hydrogen is 1 atomic mass unit. Right.
I don't have my clicker.
Okay. Okay. Waiting for Sam. There we go. So everyone's answered. Everyone answered the same. Yeah, good. Everyone answered the same, and I remember it. 6000. Everyone said carbon dioxide is heavier. I will go ahead and let Ashton, who's now here. You're the only person who's only answered once. Explain.
The 12 and the 16 will be added together for the carbon dioxide, and it'll make it 28. And then the 16 and the 1 will be added together for the H2O, and it'll be 70. So
almost right. Not quite. You have the right idea, but the wrong numbers. Carbon dioxide is going to be 12 plus 2 times 16. Right? Because it has 2 of the oxygens. And so that's 32 plus 12 is 44. Water is going to be 2 times 1 plus 16 is equal to 18. So you just didn't add the extra one when there were 2 of them. All right, so it's a very clear difference. Now, we talked about dipole attractions just a moment ago, but I'm going to start by talking about the strongest of the attractions between molecules. Ion dipole. And we have a simple example. If I put salt in water, what happens to the salt when I put it in water? It dissolves. It dissolves. The sodium is actually broken apart from the chlorine so that I'm going to have sodium ions and chlorine ions. Remember, an ion means it has a charge, it's not neutral. Why does it do that? Because of the dipole nature of the water. So with the water, the hydrogens have a positive charge, the oxygen has a negative, so this sodium is attracted to the negative sides of the water molecule. The chlorine, on the other hand, is negative. The hydrogens have positive, so the chlorine is attracted to the hydrogens. So you can see that we have the molecules are clustered around so that the positive ion is attracted to the negative sides of water molecules, and the negative ion is attracted to the positive sides of the water molecules. So this is going to form a bond between the sodium atom and the water molecules that is a bond holding essentially molecules together. And that's our strongest non-bond between atoms. It's the strongest bond between molecules. Next comes the dipole-dipole, which I've actually talked about when I talked about water. This here shows exactly why the water is bent. The oxygen atom is a much bigger atom than the hydrogen atom. And so that's why you have the bigger red than you have the little white H's. And you have the lone pairs of the oxygen, 2 electrons hanging out together, giving it negative charge regions. And so the reason it's bent is because of those lone pairs pushing the bonds around. And so that's an actual illustration of why it's bent. Now, I don't know if you guys read the kind of magazines that I have seen these in. I can't remember what kind of magazines they are. Things like radio electronics. If you look in the back, you'll find ads for different things. And one of the things that they advertise is something that will modify the water to make the water healthier for you. Has anybody seen or heard something about this? No? Well, that actually makes me a little happy. There are machines you can buy for like $400 that claim that they will take your water and they will modify the angle between the hydrogens and the oxygen. And by changing that angle, it will make the water so it kills cancer and it's just super healthy for you. You know what? That's not going to happen. That angle is pretty well specified because of those lone pairs of electrons on the water or the oxygen molecule. And the only thing that's going to change that angle is if you make it hotter. If you make it hotter, what does temperature correspond to? Raise the temperature, what are you raising? Still important when we get to chemistry. The what?
I don't know.
We're raising the average kinetic energy. So if we raise the temperature of the water molecules, not only are the water molecules going to be traveling faster, they're also going to be vibrating. And the hotter they are, the more they're vibrating. Well, those hydrogens are repelling each other, so when they vibrate more, they'll spend more time farther apart than they will closer together because of the repulsion from the hydrogens. And so the average bond angle does increase a little bit when you get hot. But of course, you cool it down and it comes right back, right? And it's oscillating between these things. You simply aren't going to be able to do some process and change the bond angle in your water. It's complete scientific nonsense. But people will part with hundreds of dollars because they read and they saw on all of these naturopathic sites that this water is going to be healthy for you. But there's no scientific basis for that. There's some other really weird myths about water. Back in '92, when I spent the summer in Japan, something that was really popular, that I think they called it pie water in Japan. They thought that you take this piece of ceramic, you put it in the water, and it changes the physical nature of the water. Makes it healthy for you, just like the bond angle thing. And not only that, all you have to do is buy your ceramic, and then if you put other ceramics in the water that you convert, it will make that ceramic so it will be able to convert more water, so you can sell your things. Kind of like a pyramid scheme almost. But what are you really doing? You're just making the water dirty, I suppose. So don't buy into those crazy water things. The last crazy water thing is that water has a memory. That water can remember being in a glacier. And it's happy. And the happy water is healthier. Yeah, there's no science to that, okay? I just want to make sure that we cover these bases. That you're not, okay, this is one that my beloved wife thinks might have some validity. If you heat water in a microwave, what does it do to the water? Okay, it makes it hotter, makes it vibrate more. And then when it cools down, what's the difference in the water that you heat in the water microwave and water that you heat it on a stove? There is no difference at all. And yet there's this meme, this 8-year-old student for her science project used water heated in the microwave to pour on these ones, and other water to pour on these ones. The ones that use the water heated in the microwave didn't grow. And see, water heated in the microwave is bad for you. Microwaves are dangerous. Once again, there is no science behind that. And many people, if you look at Snopes, the people at Snopes, who I know are not always accurate, they actually, either them or they found somebody who reproduced the experiment and showed, yeah, that's not what really happens. I wanted to do that myself, but we didn't. I know somebody who threw away their microwave because they were worried that it would cause health problems by microwaving your food. Okay, moving on. So we talked about the ion dipole attraction, then the dipole attraction that I actually talked about first. The next weaker, so this is the strongest, was of our molecular attractions. The strongest was the ion dipole. Then the next was the dipole-dipole. We're going down to weaker as we go down this list, is a dipole-induced dipole. Induced dipole is something that we've already studied. When you took the balloons in lab and you rubbed them on your head, those balloons became charged. They had negative charge. When you put them up to the wall, what did it do to the wall?
It stuck.
Okay, it stuck. What did it do to the wall that would make it stick? Okay, because you had negative charge on the rubber, it repelled electrons in the wall, but that left a net positive charge close to the rubber. Hence, it was attracted to the part that was close, repelled to the part that was far. But because the electric force is inversely proportional to separation squared, the farther charges didn't have as big effect. So you induced a dipole, that is, you made the charge separate in the wall, and then you had an attraction between the charged object and the uncharged object. So that's what a dipole-induced dipole is. So an example here, here's a water molecule. Water molecule is completely nonpolar. But if you, or not water, that's oxygen. You guys really should give me grief when I mistake something like that. So the oxygen molecule is completely nonpolar. You bring it close to something that is polar, there's the water molecule, and these negative charges on the water molecule are going to push away the negative charge. So now you have an induced dipole for the oxygen molecule. Because that induced dipole, the part that's closer is positive, positive is close to negative, that's attractive, and now you have a weak attraction between the induced dipole of the oxygen molecule and the permanent dipole of the water molecule. So we're getting down to weaker because you had to bring something with the charge separation near something that wasn't, and you cause a change there. Now that's our next to weakest of the forces that hold molecules together. Anyone want to guess what the weakest one will be? Here's two completely nonpolar molecules. Each one has an electron cloud around it. So each one has a negative exterior and a positive center. When I bring them close to each other, what are the negative charges going to do? Negative does what? Repels. So if I force them close to each other, there's going to be a force that pushes the charge away. So what I can have happen is I will have this one here, will have its charge redistribute, so it's more negative over here, and more positive over here. That's an induced dipole. What induced it? It was something neutral. And so I'm going to have this here will now, once that has formed that dipole, this one will form a similar dipole. And the induced dipole is now attractive. So I brought them close and the charge was redistributed to make them both into induced dipoles with attractive force. Now that's a really, really weak interaction. But that's the last of our molecular interactions, the dipole, induced dipole. This is showing it with argon. Argon is in the right column, the noble or inert gases. Argon's not supposed to do anything. And yet if you bring the two argon molecules or two argon atoms, because they're monatomic, close to each other, you can make them induce a dipole on each other and form an attraction. So here's a summary of those four. The strongest, the ion dipole. The ion is naturally charged. The dipole naturally has a charge separation. Why don't I have ion? Well, because that would form an ionic bond. So ion dipole is our strongest of these molecular attractions. And then you have dipole because they both naturally have the charge separation again. Then the next two are much weaker because you have induced dipole. A dipole causing an induced dipole, or the bottom one, induced dipole. Both of them were nonpolar. You brought them close and it forced them to become dipoles. Which one of these forms between water? Water molecules form one of these four types. Yes. So this is what water forms. And so that's relatively strong compared to these others. And because of that relative strength, water forms a liquid at room temperature instead of a gas. A liquid because it has these forces holding the molecules together. And it freezes at a higher temperature than it normally would because of these forces. What's an example of the ion dipole? The example we used. I put salt in water. Salt is actually a generic term that means what happens when you put an ionic compound in water. It's actually, you put an acid and a base together and the salt precipitates. But we haven't learned acid and bases yet. But salts are ionic compounds. And then dipole, induced dipole. The example we used was water and oxygen. And notice I said oxygen molecules, that's O2. And then the weakest, the induced dipole. So here's some information to help us see how these work out. So things that are going to be polar, what kind of molecular bonds are they going to form? If you have polar molecules, which type do they form? Polar molecules, things that form a dipole. If I have things that are polar that form a dipole, what kind of bond are they going to form together? Covalent was the term for bonds between atoms. Now we're talking about bonds between molecules. That is, it's a tricky thing to make sure you keep separate. Right? It's something I have not kept separate in my mind. Okay.
So covalent is between
atoms. to form a molecule. And now we're looking at bonds between molecules to hold them together to make a solid or liquid. So if I have dipoles, which kind of bond am I going to make? Dipole, dipole. And so that should be our second strongest. The ion dipole would be the strongest. So if we look at this table, we can see that the boiling temperatures for the polar substances are higher temperatures than the boiling temperatures for the nonpolar substances. Why are they higher temperatures? Because they form dipole-dipole bonds between the molecules, making it so it takes more energy to separate them. So we see water has a boiling temperature of 100, hydrogen fluoride 20, ammonia minus 33. Okay, that's a pretty low temperature for ammonia, but compared to nonpolar molecules like hydrogen, oxygen, nitrogen, and a couple other carbon dioxide, you see these here are really cold because they're not held together very strongly at all. If they're nonpolar, if I have two nonpolar molecules, what kind of bond is going to hold them together? If I have two nonpolar molecules, what kind of bond is going to hold the molecules together? Induced dipole, because neither one has a dipole moment. You're going to have to induce it on both. That's the very weakest. And so that's why you have a much lower boiling temperature for the nonpolar ones, because they're hardly held together. It boils when you're able to take the molecules apart from each other. If they're hardly held together, a much lower average kinetic energy is enough to take them apart. I don't know why this question comes here, but I kept it because I like it. Is it possible for a fish to drown? I know this seems like a biology question, doesn't it? Oh, it's not allowing you to answer. Now it's allowing you to answer. Sorry about that. Thank you, Ashton. First answer. Okay, everyone's answered. 132. Hey, it stayed this time. All I have to do is say them out loud and they'll stay, right? Okay, we had some variation here. Let's turn to Leslie. What sayest thou, Leslie?
Well, I was not really sure. I was kind of caught between B and C, but then I was like, okay, well, to me, C made the most sense because when I looked at B, it said contains too little oxygen in the water, but it's H2O. Like, that's already, like, you know, it's in the formula of its water. It's going to have oxygen. So I just put that it's 88% oxygen by mass.
Okay. Now, this is a really important chemistry question based on what she answered. Water is indeed mostly oxygen, right? H2O. That means it has 16 atomic mass units of oxygen for 2 atomic mass units of hydrogen. So 2 out of 16 hydrogen or 2 out of 18, excuse me, or 16 out of 18 oxygen. It's 88.8 repeating, so I really should have said 88.9. So the water molecule is, let's just say 89% oxygen. But when you breathe, you're not breathing oxygen atoms. You're not separating oxygen from the hydrogen atoms. You're breathing oxygen molecules. So the oxygen atoms in the water is not helping you with breathing at all. It's the oxygen molecules, the O2s. So her answer was incorrect because that's not what you breathe. right? What you need to survive is the O2 molecules, not just oxygen atoms attached to something. I mean, quartz, silicon dioxide, it's got lots of oxygen in it. You're not going to ever survive by trying to put quartz in your lungs. So that's the reason that one's not the correct answer, is because it's not the oxygen atoms that we breathe, it's the oxygen molecules. And likewise, fish don't breathe water. They collect oxygen from the water, but that needs to be oxygen molecules. Why do we have oxygen molecules in water? What's the chemical formula for water? We just had it, just a reminder. H2O. So we have these H2O molecules that are polar molecules. Oxygen molecules are nonpolar. But you can form a very weak bond between the nonpolar oxygen molecules and the polar water molecules, so that you will have some oxygen that is held to water molecules. And that's what the fish are breathing. They are taking in the water that is holding some oxygen molecules and then processing those water molecules that are being held to the water molecules. Question?
Is that why you have to change fish's tanks, like the water that they have? Like that's...
If you never changed the water and you did not have an aerator, right? Aerator is something that's bubbling air in there. Then yes, they would simply take out the O2 and then you would have water without any spare oxygen for them to breathe. And so then they would suffocate. If you don't have the O2 in there, they would suffocate. And so they would suffocate when the water contains too little oxygen molecules. So yeah, that's why you change the water, use the aerator or something. When the water is not moving, well, what difference would that make? You wouldn't be moving around and bringing in oxygen molecules. So these two, either one would have been relatively correct. Dealing with, they need to have the oxygen, molecular oxygen, bound to the oxygen molecules. I've got to talk about Teflon. I know you guys want to leave. Teflon is made of carbon and fluorine. Fluorine is the most electronegative of all molecules. Hence, fluorine is actually really dangerous. Fluorine gas, you don't want to mess around. It will cause all kinds of problems. And yet, we make Teflon in our food preparation materials. We have Teflon-coated pans. And Teflon has lots of fluorine. A lot more fluorine than it has carbon, so it's primarily fluorine. It's a polymer, which means you have a long chain of carbon atoms, and each carbon atom has two fluorines on it. And the question that you have to ask is, why would we subject ourselves to this crazy, dangerous fluorine atom? Because we're out of time, the answer is simple. These fluorine atoms are bonded to carbon atoms. They're not free. Just like you can't breathe the oxygen atoms in the water molecule, the fluorine atoms that are bonded to the Teflon aren't going to interact with you. In fact, they're very inert because they form a non-polar compound. The Teflon is non-polar. Because it's non-polar, it's not going to form dipole-dipole or dipole-induced dipole. The only thing it can form is induced dipole bonds. But fluorine is a very small atom. Why is it small? Well, because it has such a large electronegativity, it actually pulls the electrons in, making it small. And because it's small, it's very hard to induce a dipole on it. So those fluorine atoms have very little induced dipole action, hence you have basically no molecular attractions between the Teflon and other molecules, hence our non-stick coatings. Compare that to something like saran wrap. Saran wrap, we have, I believe it's induced dipole. It says in your textbook. That forms when we bring that to glass. And so that's a type of molecular attraction that holds your little plastic wrap on your dishes. Okay, we're out of time. Have a great day, and I'll see you on Wednesday. And yeah, I'll put. Did I put up a homework already? I did? Okay. I still probably should